All right, this should be for Thursday's class. Thursday, February 6th, apparently. And not at the end of class, but maybe half or 2/3 way, we talked about how to find the center of mass of a truck. And then we talked about the Lawrence Winery collapse, and we talked about in Kansas City the Skyway collapse. And then there was a section review section to work. And I don't know what page that was from. 288 maybe. Guess I should, shame on me for not having that ready to go. And we got to jump around in here. I think it was 289. If you're on page 289, and you know where to find that in Google Classroom, in textbook chapters, we're in chapter 8. 289, there's a whole page, but you can't really do the ones on the bottom. This chapter has a lot of good problems in it, but you don't want to try to teach it in the sequence they've got. So you got to sort all that out. So we will do 1 through 5. And question 1 on page 288 says, where should the supporting, you need to look at these on the paper, not write down what I have, because that doesn't make any sense. You got to read the question. Where should the supporting pivot be located on the object in figure 8-9 to produce the following? A positive torque and a negative torque and no rotation. So if the pivot is all the way out here at A, it's probably going to rotate that way. If the pivot is all the way out here at G, it's probably going to rotate that way. So you want the pivot to be in a location such that the torque this way and the torque that way are equal. And you got a 50 Newton force on the left and a 150 Newton force on the right. Well, off the top of my head, one force is 3 times larger, so one lever arm needs to be 3 times longer. So if the heavier mass of 150 newtons has a 1 unit lever arm, the 50 Newton mass is going to have a 3 unit lever arm, whatever that unit may be. So they're going to be in a 1-to-3 ratio. Okay, we aren't going to view a video involving the Skyway collapse. You can do that though. There's good ones out there. So the torques have to be equal, the twisting forces. So that means the force times radius has to be equal, force times radius has to be equal. But one of the forces is 3 times larger, and it will have 1/3 the radius. So the heavier 150 Newton one has a unit of radius, and it doesn't matter what that unit is. This is just 3 times that unit on the lighter weight. And if you do that, location F, I don't know what this says in here, but location F is 3 units one way, 1 unit the other. You gotta count them off at the top, the hash marks up at the top. So from the weight to F looks at 1, 2, 3, 4, 5, 6. So there must be 18 the other way. So this says 6 hash marks, this says 18. That's what those chicken scratches are. Okay, number 2. Determine the approximate location of center of mass for the following objects. A meter stick at the 50 centimeter. A bowling ball. Well, if it doesn't have holes drilled out for the centers, it'll be right at the center of the bowling ball, the center of mass, the center of gravity. An ice cube, more or less, if you connected all the diagonals together where they crossed in the center. A donut, if the donut is round, it'd be in the center of the donut where there's no material. And a banana, well, not within the banana perhaps. This must have been telling where if you put the fulcrum at these locations, if you'd have a clockwise or counterclockwise rotation. If it could move. All right, so what I'm trying to do. is this. So I told you where those are, but you'd have to write them down. Number 3, and I think Julia Sumner Miller deals with, if you finish watching that video like you're supposed to about center of mass, I think he talks about the banana and the donut. The student says the moment of inertia and the mass are the same thing. What's wrong with this reason? Well, translational inertia and mass are so close to the same thing that I have trouble describing the difference with them. You can practically make them mean the same thing. It'd take me a while and even a little bit of research, but there is a distinction between them. It's not significant though. But if something's got a rotational inertia to spin versus translationally move this way or that way, that's not related to mass. Well, it is related to mass, but it's also related to the radius. So it's not the same thing. Okay, so because we are going to get there, we actually haven't covered it yet, but moment of inertia is mass times radius squared times something. If that something is 1, you've got a hoop. If it's half, you've got a disc. If it's 2/5, you've got a sphere. And boy, we're going to talk about that. So the fact that it has a tendency to not want to spin one way or the other, it's got an inertia in that regard. That's related to mass, but it's way more related to radius because the radius is squared in there. That was number 3. Number 4. So you need to have something written with that. On 1 through 5, there is no net torque, and so these aren't going to accelerate angularly to one way or the other. So we can go ahead and talk about this. Number 4, identify which, if any, conditions for equilibrium hold for the following situations. A bicycle wheel rolling along a level highway at constant speed. So if your speed is constant, there's no acceleration, angularly or translationally. And that's what I think they mean for equilibrium. Nothing's changing there. A bicycle parked against the curb. Well, nothing's changing here because the motion remains constant. And in B, nothing's changing there because the motion remains constant. It's just that this motion is 0 and this one is not. But that distinction is not very important. Now, Newton's first law deals with translational motion. It's a little more complicated when it's rotational. It still applies, but we're not going to discuss that, I don't think. But my point is, Newton's first law, objects at rest tend to stay at rest, objects in motion tend to keep that motion. That sounds like two statements, it's not. A better way to say it is objects have an inertial tendency to keep the motion they have. If that motion's 5, they'll continue to translate at 5. If that motion is 11 meters per second, they'll continue to translate at 11. If their motion is 0 meters per second, it continues to translate at 0. It's more complicated when spinning, but if there's no change, it's still equilibrium. Number C, the tires on a braking automobile that is still moving. Okay, I guess there's multiple discussions you could have on it, but let's say the car is braking and the tires are slowing down and the translational motion is still going, but it's slowing down. It's still moving, but it's slowing down. Well, that system is not in equilibrium because you got acceleration. So as long as you don't have the brakes locked up and the tires are still rolling but slowing down their rotation rate, and the car is slowing down translationally, you don't have equilibrium. Now, if the tires are locked up and you're screeching, then the tires have a rotation of 0 and they're at equilibrium, but the car does not. Football traveling through the air. Well, it's accelerating. I think, okay, so let's say the football is thrown and it's spinning in a spiral. Well, that spiral may have a constant rate and a constant direction, which is a different thing, but that's a factor too. That could be at equilibrium, the rotation, but it's accelerating translationally in the y-axis. It's going up and down. Interesting thing is the x-axis is a constant velocity. It is at equilibrium. But when you add all this up, basically because part of it is not in equilibrium, then the answer is no, it's not in equilibrium because not all of it is in equilibrium. Number 5, you got a 40 Newton board, got 2 kids on it. One weighs 510, the other one weighs 350. The support is under, the fulcrum is under the center of mass. And the 510 Newton child is 1.5 meters from the center. Where should the 350 Newton child sit to balance the system? So you have to make the torques equal. And the way that's going to look is the board's 40 newtons, but right there where the fulcrum is, that's where the center of mass is, so the board's not going to come into play. The 510 Newton kid is 1.5 meters. The 350 Newton kid is less than this is, so it has to be farther out to get the same twisting force, because it's force times radius equals force times radius. So if the force is higher, the radius is less. If the force is less, the radius is higher. As a matter of fact, you could set up a ratio of these two, and then you'd have a ratio of the radii. It might be an inverse of them, but. So just set it up as this torque equals that one, force times radius equals force times radius, 350 times an unknown equals 510 times 1.5 meters. And radius comes out to 2.2. And it wants to know on B, how much does the support exert on the board? Well, the support exerts 510 and 350 and 40, all of the weight, because there's only one support. Okay, we'll stop with that one, and this might be the end of things for today. You got to watch that landing gear video. Between these two, I might call this a day, so we'll find out.